Okay, so let's look at proposition 3. It says if y1 and y2 are two solutions of the second order differential equation, this guy here, on interval alpha to beta, then y1 and y2 are linearly dependent if and only if the Wronskian is 0 on alpha beta interval. So this is an if and only if proof, so we have two directions to show. So let's start the proof. Okay, so again, it's an if and only if statement. That means there's two directions to prove here. So we're going to assume that y1 and y2 are solutions of this guy up here, and they're linearly dependent. We're going to suppose y1 and y2 are linearly dependent, and we're going to show now that the Wronskian is 0. Okay. So now y1 and y2 linearly dependent. That means that y1 is basically a multiple of y2. So let me write that here. Alright, so this implies then y1 equals say c times y2 for some c value. Okay. Now let's take derivative on both sides. So it follows then that y1 prime is going to equal c y2 prime. Now let's recall the definition of Wronskian. Let me write it here. So here's my definition of Wronskian. It's y1 y2 prime minus y1 prime y2. Now we're going to make the substitution for y1. We'll write cy2 in place of y1 here and cy2 prime in place of y1 prime here. So doing that we get then. So making the substitutions for y1 here as cy2, which I've done here, and in place of y1 prime writing cy2 prime here. So you can see right here this becomes 0. Okay, so we've shown that if y1 and y2 are linearly dependent, then the Wronskian 0. So we've shown this direction. So now we have to go this direction. So this direction we're going to assume the Wronskian is 0, and also that y1 and y2 are solutions of this differential equation. Then we have to prove that y1 and y2 then will be linearly dependent. So let's do that next. Okay, so for the other direction, we're going to suppose y1 and y2 are solutions of this differential equation up here. The Wronskian is 0. So we need to show that y1 and y2 are linearly dependent. That would mean in this case that y1 equals some constant times y2. Okay, so let's look at some cases first. So case 1, suppose y1 equals 0 on alpha beta, so just equal to 0 for all x on alpha beta. That implies then that, let me write it here, that y1 then will be 0 times y2. So again, this implies then y1 would be 0 times y2. So be done with that case then. So the next case would be that y1 is not equal to 0 for all x on this interval. So let's look at case 2 next. Okay, so for case 2, we're going to assume then that the y function is not equal to 0 on alpha beta. That means there's going to exist at least one x value, we're calling it x1, between alpha and beta, in which the function is not equal to 0. Okay, so we're going to assume that. Okay, I'm out of space, so I'm going to erase a few things and we'll keep going. Okay, so now I'm going to use the fact that y1 is continuous. It's continuous because the first and second derivatives exist, because we're assuming it's a solution of that original differential equation. So it's continuous on alpha beta. Implies there exists a delta such that y1 of x is not equal to 0 for all x in this interval here, which I'm calling I subscript delta. So let me explain this a bit better in the picture here. Okay, so here's my picture. So we're assuming that y1 of x1 is not 0. So here's x1, say, and here's the point. I'm assuming it's positive here, it's fine. So continuous means you have to be able to draw the graph without lifting your pencil intuitively. That's what it means. So you can see that if I drew my graph in here, I want to make it 0 side of the graph as quickly as possible. I guess I could go like this, perhaps in there, maybe down here. But you can see there's going to be a part here where the function would not be 0. That's what I'm calling my I subscript delta here. So it'd be in there. So it'd be some delta. So that's the idea. Okay, so let's keep going. Okay, so next let's look at the derivative of y2 over y1. So we're going to have to use the quotient rule. So here's the quotient rule here. So it'll be derivative of top function times bottom minus top times derivative of bottom divided by bottom squared. And notice here, this numerator up here is actually the Wronskian. So let me write that here. Okay, so again, the top part here is the Wronskian divided by y1 squared. And now we're assuming that the Wronskian is 0. That's going to make the derivative 0. It'll be 0 on top here, so the whole thing will be 0. So hence we can say then, okay, so this implies that y2 over y1 then is a constant, because when we took the derivative we get 0. So if the derivative of a function is 0, it means the function is a constant. So therefore our y2 over y1 must equal a constant on our interval I. Okay, this implies then multiplying both sides by y1, you're going to have y2 equals cy1 on our interval I. Okay, so in particular then we have then that y2 of x1 equals cy1 of x1, and if you take derivative on both sides here and then stick in x1, you'd also have y2 prime x1 equals cy1 prime x1. Alright? Okay, so this implies then that y2 and cy1 are both solutions of the initial value problem. Again, we're assuming that y1 and y2 are solutions of this differential equation here, its original differential equation. Okay, so therefore we have two solutions of the initial value problem. So by uniqueness theorem, the two solutions must be the same. So by uniqueness theorem then, we must have that y1 equals cy2 on all of alpha beta. So you've just proven it up here for the I interval, which does not include all of alpha beta up here. But now by uniqueness theorem we're able to extend it all the way to alpha beta. Okay, so we're done because this implies that their y1 and y2 are linearly dependent. Let me write it here. So hence we've shown that y1 and y2 are linearly dependent, I guess, on our alpha beta interval. Okay, so we're done. Okay, so let's take a look now at a corollary to this. Okay, so here's corollary 1. So a corollary just means that it's something that follows directly from something you've already proved. So let's see why this follows from. It's going to follow from proposition 3. So let's read the statement here. So if y1 and y2 are solutions of this differential equation again on alpha beta, then y1 and y2 are linearly independent if and only if the Wronskian is not 0 for some point in alpha beta. Okay, so I claim it just follows directly from proposition 3. So if we look at the statement of proposition 3, it says that y1 and y2 are linearly dependent if and only if the Wronskian is 0 for all x values on alpha beta. So pretty much as soon as you can find one place where the Wronskian is not 0, then that would imply linear independence from proposition 3. Just look at the negation of the statement in proposition 3. Okay, so it just follows from prop 3, so we're done. Okay, so let's leave it there. We'll pick it up with theorem 5 in the next video. Okay, so let's leave it there.